So now let's take a look at how you do karnaugh maps if you have more than two variables. So far we just looked at functions which had two inputs and one output. Now let's take a look at what you do if you have multiple inputs. So the key here is you need to order your variables across the top and the side such that only one bit changes between each row and column. This is called gray coding. Let's take a look at an example so we can see how this works. So here we go, I've got four inputs. A and B are across the top in blue, and C and D are down the side in green. And look at how the numbers go through across the top and along the bottom. So we go from 0, 0 to 0, 1. That's good, only one bit changed. But then we don't go to 1, 0. Instead, we go directly to 1, 1. And why is that? Well, when we go from 0, 1 to 1, 1, we only change one bit. And then again, when we go from 1, 1 to 1, 0, we only change one bit. So the important thing to remember is we've changed the orders here such that we only change one bit in each column. And we have to do this so that we can circle things when we do our karnaugh map. Now what do these rows and columns mean? Let's take a look at the inputs for C and D along the side. So here's C and D, and here's one of the inputs. So here we have 1, 1. This means both C and D are true. So everything in this row is C and D. Up here where we have 0, 0, this means neither C nor D is true. So we have not C and not D. Similarly, here we have not C and D, and C and not D. So now that we've got all this information, doing a karnaugh map is basically the same with more inputs as it is with two inputs. Let's take a look. So here's our function. We can see all the ones. And let's circle this box in the middle. So this is power of 2. We have 4 ones in it, and we're going to circle it. So what's the logic equation for this? Well, if we look at it, that's these two columns. So what do these two columns have in common? And these two rows. And what do these two rows have in common? So our logic equation is going to be the AND of these two things, the rows and columns. So if we take a look at the columns, we can see that they both have a 1 for B. So these two columns are B. And over here in the rows, these two rows both have a 1 in the D place. So these are both D. So what this tells us is this orange part is B and D. And we saw that by drawing the box and looking at what it corresponds to in the inputs in the rows and columns. Now let's draw another box. So now we're going to draw this one up here. And this one's very similar. It's going to be the same B term, but now the term we're going to have along the rows is going to be not C. Because if you look on the side here, you can see that for these two rows, the thing they have in common is not C. So this is not C and B. And then we have another box with 4 entries in it. And this one is just in one row. And so this one row is not A and B. And you can see that if you look up at the top here, not A and B. So not A and B. And so that tells us what our function is. It's these ORed together, which is the same function as what we have written down below. So you'll notice that the boxes overlapped here. And that's not a problem, because all that you have to have is all ones in the box. When they overlap, it just means you may have defined your output in multiple different ways, but it's not a problem for correctness. So, to summarize karnaugh maps allow you to take a truth table and convert it to gates. And this is important because we describe functions' behavior in terms of their truth table, but we need to build them using gates. So remember to circle the largest groups that are powers of 2, so you get the simplest equation. The groups are allowed to overlap, and remember the input should only change one bit at a time. So if you have more than 2 inputs, you need to use gray coding to order them. If you have outputs you don't care about, you can put X's in your karnaugh map, and then you can circle those X's as if they were 1s, or treat them as 0s. However, the thing to keep in mind here is that this sort of stuff is done by computers these days. So all the modern tools, including Logic Sim, which you use for your lab, will convert truth tables into logic gates for you. The reason we're looking at this is so you get an understanding of how you build things up.